Good day and welcome back to the second part of our discussion on directional derivatives, where we will think about the computational aspect. So when it comes to computing directional derivatives, we need to think essentially of three quantities of interest. We have a function, a point at which we are taking the directional derivative, and a unit vector in the direction of the desired rate of change. And as indicated on the previous video, the fact that it is a unit vector is of key importance. So we have the following formula for calculating the directional derivative. So the directional derivative of the function f in the direction of a unit vector u is given as follows. It is the partial with respect to x at xy times a plus the partial with respect to y times b, with note from directly above, u, the unit vector, is given by a, b. And sometimes it's worth going through various level of details to see where something comes from. In this case, I'm just going to give you a small kind of indication of where this formula would come from, and note that the book includes more details. So this formula for the directional derivative can be found if we apply the chain rule to the following function. We'd have to apply it to the function g of h, which is defined to be f of x plus ah, comma y plus bh, with g prime of 0 would be the directional derivative of the function f at the point xy in the direction of u. So in a sense, it's just measuring kind of that rate of change if you're at a specified point and you move in the direction given by the vector a, comma b. Now in terms of computations, let's write this a bit more conveniently. We could really think of this as a vector given by partial with respect to x, comma partial with respect to y, our two components, dot it with a second vector whose components are a and b. And it turns out this first vector is something that we frequently encounter, and we'll revisit it again at the end of the course, and it is referred to as the gradient of f, and we are dotting this with the unit vector given by u. And what we end up with on this bottom line is the typical formula and approach we will use to compute the directional derivative. And just to make sure we're all on the same page, that bit of notation we introduced is something we refer to as the gradient of the function f. It is a vector whose first component is made up of the partial with respect to that first variable x, and the second component is made up of the partial derivative with respect to that second variable y. So let's go ahead and apply this idea to a nice concrete example. Let's find the directional derivative of the given function at the point 0, 1 in the direction of this vector u. So the first thing I want to check and note is that u is in fact a unit vector. So the magnitude of u would be the square root of the sum of the components squared. So root 3 over 2 squared is 3/4, plus 1/2 squared is 1/4, and the square root of 1 is 1. So check, u is in fact a unit vector. And I do want to observe, if u is not a unit vector, you have to figure out or find a unit vector in the direction that we are given. Now that we know u is a unit vector, we need to find the gradient of f. So the gradient of f is a vector whose first component is f sub x and whose second component is f sub y. Looking at the function of interest, the partial of f with respect to x is 2x, whereas the partial with respect to y is 2 times 1/2 y, or simply y. That leads us to the directional derivative of the function f at the point 0, 1 in the direction of this unit vector u. This would be the gradient of f evaluated at that point of interest, 0, 1, dotted with the unit vector. The gradient vector when x is 0 and y is 1 is 0, 1, dotted with root 3 over 2, 1/2. In the dot product, remember we multiply together the corresponding entries and we sum them up. So the directional derivative in this case is simply 1/2. And note that this really is a very standard computation. One kind of immediate generalization to this in terms of the types of questions we might ask you would be to find a directional derivative involving a function of more than 2 variables, which is perfectly reasonable. Let me go ahead and note, just to make sure we're all on the same page, for a function of 3 variables, the gradient vector associated with it would actually be now a gradient vector with 3 entries. Partial with respect to x, with respect to y, and with respect to z. And we can generalize to a function of as many variables as we would like, though we typically go past 3 or possibly 4. For the problem of interest, we're given a function of 3 variables, a point, and a direction. What I would like you all to do is to pause the video, take 3 or 4 minutes, and come up with the desired directional derivative. Okay, so assuming that you have taken the time to come up with this desired directional derivative, I'm going to begin by noting, and hopefully you did as well, that this direction is not a unit vector. So the first thing we might want to do is get a unit vector representing that direction. And recall, if you have a vector and you want a unit vector in its direction, you simply multiply it by 1 over its magnitude. And the magnitude of this given vector would be 1 over the square root of the sum of the components squared. 5 squared plus 1 squared plus minus 2 squared. And it's not maybe the most convenient or nicest looking vector we've seen, but if we multiply through each component by 1 over the square root of 30, we would have 5 over square root 30, 1 over square root 30, and minus 2 over square root 30. And the big important characteristic of this vector is that this is now a unit vector by design. The other key ingredient we need for the directional derivative would be the gradient vector. So for the gradient vector, it will be a vector with 3 entries. Its first entry would be the partial with respect to x, then y, then z. So a partial with respect to x, we treat the y and z as constants. Working left to right, we would have e to the y plus z e to the x. For a partial with respect to y, we treat the x and the z's as constants. So x e to the y plus e to the z. And a partial with respect to z, y e to the z plus e to the x. And just as a reminder, as we're going through computations, maybe in this case partial derivatives, which we will do frequently in upcoming sections, if I've gone through something a bit too quickly or you need a break, liberally make use of the pause button. Feel free to rewind, look at examples in the book, look at the completed note packet online. We have lots of good resources. So putting this all together, the directional derivative of interest, now at the point 0, 0, 0, is given by the formula gradient of f at the origin dotted with u. If we go ahead and substitute in x, y, and z all being 0, what we would end up with is 1 plus 0, 0 plus 1, 0 plus 1. That is, the vector is determined by 1, 1, 1, and we're dotting it with 5 over root 30, 1 over root 30, and minus 2 over root 30. And to find a dot product, you multiply together those corresponding entries, and we add them up. So you would have 5 over the square root of 30 plus 1 over the square root of 30 minus 2 over the square root of 30, and 5 plus 1 minus 2 gives us 4 over the square root of 30. And the 4 over the square root of 30 is that desired directional derivative. This completes the material for this second video of investigating the directional derivative from the computational perspective. In our third video, we will investigate several applications of the directional derivative. So stay tuned and take care.